Hi everybody, my name is Amy. I'm the head tutor for mathematics at Pinnacle Coaching. So today I've got part 2 of the series for you from geometric application of calculus, and today's focus is going to be on maximization and minimization problems. If you haven't seen my previous video, please have a look. I've left the link down below. That's on curve sketching. You might find that very helpful and you might want to do that before watching this one. Alright, so what is maximization, minimization problems? So let me show you. This is actually an example from a past HSC question from 2015, question 16C. It's actually the last question in the mathematics exam. So this is the type of problems we want to tackle today. But before we jump into it, I'm going to just explain some theory behind these questions. Today, I'm going to talk about how to tackle maximization and minimization problems. Before I jump into that, I want to give you some context around how is this topic examined usually. In the HSC, it's always at the end of the paper. So the last two questions, question 15 and 16. So they tend to be more difficult, time consuming, and just be mentally prepared for that. So when you watch this video, if you feel at any point you're not fully following, pause, maybe rewind it, or just have a go and try to follow along. And if this is in your upcoming assessment, it's most likely to be the last question. So just be mentally prepared for it, and so slowly take it step by step and break it down into steps. Alright, so on the subject of steps, let's talk about the two core steps in all of these questions. So, the first step is always around building an equation for the thing you are trying to maximize or minimize. So I've sort of generalized this terminology thing because it does vary from question to question. So very typical things maybe like areas, volume. Sometimes I've seen question which is like a cost equation, profit equation. You may also see like a distance, time, etc., etc. Okay, so it can be quite a variety of things, and I will elaborate on how to do step 1 in the next segment. Second step is to find, once you found the equation, the second step is to find the global maximum and global minimum. Now I'll say 90% of cases you're looking at the turning point. So it could be just simply a max or minimum turning point. So remember, last week, how do you find maximum and minimum turning points? That's all about finding the first derivative. So f dash x, solve it to 0. You can use a table of values to test. Okay? In the application of calculus to these type of questions, you still need to show the nature of the turning point. You can do the table of values, or I haven't really mentioned this option when we're curve sketching, you can use the second derivative. So I'll discuss how to use that today. There are 10% of cases where the answer is at the endpoints of the domain. Okay, I mean they are quite rare, but if they do appear, usually I will say 95% of the state will not be able to answer this. So if you're the top 5%, let's shoot for that mark. So I would like to elaborate a bit more on that step 1, how to build the equation for the thing you want to maximize and minimize. I will say a lot of the difficulty in these type of questions is actually able to interpret the information and build the equation the question is asking for. Now before I go into it, I just want to take a pause. In typical exam questions, as I will show you later, often the equation is sitting in the question. So if you can't answer the first part, which is the building the equation part, I really want you to go on to the second part, which is the differentiation part. It's already there, yeah? Don't lose out 5-6 marks because you couldn't do the first part and just left the rest blank. I've seen that all the time, and it's not a good way to approach an exam. The best way is, okay, I tried part 1, I couldn't get it, I'm going to use that result and answer parts 2 and 3. Yeah, so at least you get 3 out of 5 marks or 4 out of 5 marks. So you sort of get the point here. Alright, so back to how to approach step 1. Typically, there are two things to consider. First, you have to ask yourself, what exactly are you maximizing or minimizing? I'll say broadly, there are 3 categories of things that you will look at. The most common one, and I will say about 70% of the cases or questions you encounter in this area, are area and volumes. Now, in the course, you're actually not expected to know your equations for a lot of the volume formulas. So if they do test it in the HSA, they often give it to you. But in assessments, your school assessments, your teachers may not give it to you. So I still strongly recommend you remember it. So the typical ones people often forget include cylinder, so radius, height, so pi r square h. And then we've got your cone. Okay? Now, the easy way to remember cones is always a third of the cylinder. So a third pi r square h. And then finally, the sphere. Let's say it has a radius of big R. 4 on 3 pi r cubed. Okay, so those are the common ones that gets examined. So I'll show you the formulas here in case you need to use them. Now, another very commonly tested, I'll say about 20% of the cases I see are the speed, distance, time relationship. So you first need some clarity around, are you trying to maximize or minimize the speed or time? Okay, usually it's not really about speed. And remember the relationship between speed, distance, and time. It's not speed, it's distance on time. Okay? And then finally, it could be a coordinate geometry relationship. So I'll say 10% of cases are coordinate geometry cases. And that's where you use your coordinate geometry formulas like distance formulas, perpendicular distance formulas. And usually it's got something to do with distances. So that's pretty much all there is to it. I'll say this covers majority of the things you will encounter in this area. But even though I summarized everything, just be aware often it's like a whole page of story around what is happening and what is the thing you're trying to maximize or minimize. And I'll say that's where the difficulty is, question interpretation. Okay, so after you've built the expression for the thing you wanted to maximize or minimize, there might be multiple variables involved. And this is where you have to look for a relationship between your variables so you can make it a single variable expression before differentiating it. So some common places to look for that relationship includes, firstly, look at any constraints in the question. So sometimes, for example, if you're just trying to maximize the volume of a cone, it might be, the cone is restricted or the cylinder is restricted to just 500 centimeters cubed, okay? Another common example where you can find relationship between your variables are similarity relationships, which often comes in the form of similar triangles. And finally, something that's often forgotten by most students is the good old Pythagoras. If you see right angle triangles, try Pythagoras. See if you can link your sides together and hopefully create an expression you can use to link your variables together. Okay, so now that you've understood the basic steps involved in the maximization and minimization problem, let's come back to the HSC question I showed you right at the beginning and apply those steps to this question. Now, before I go into the question, let's have a look at the diagram. So in this diagram, what you have is a cylinder inscribed into a cone. And as we read the question and find out, this cone is actually fixed. It does not change. It is the cylinder that is changing, and we are trying to maximize the volume of the cylinder. So imagine you can change X and Y and make it wide but short, or tall but skinny. Okay, so there are different ranges of X and Y value that we can put in, and it will change the size of the cylinder. But we're trying to find the specific measurements that will give us the maximum volume. Alright, so coming back to the actual question itself, let's have a read. So the diagram shows a cylinder of radius x and height y inscribed in a cone of radius r and height h. h, where r and h are constants. So the key point here is the fact that they're constant. Okay, that is your sort of flag for saying, all right, that doesn't change, that's all fixed. And it's the inside, so coming back to the diagram, the cylinder that is changing, okay, not the cone. And that actually having clarity will help you when you try to differentiate the expression later. Alright, so part A, we're going to try to show the volume of the cylinder can be written in that format. So let's do this together. Alright, so let's break down the diagram. In these cylinder inscribed in cone situation, quite often you can take a cross section of the solid, and actually what you get is this type of shape. It's like a right angle triangle with a rectangle inscribed into it. So literally I'm just only taking half of the cross section, the other half is actually just a reflection. We won't be looking at that. Now, I've also written up what we are trying to show. Always keep in mind what you're trying to show so you know you're going down the right path. Alright, so let's have a look. So typically, this type of question uses similar triangles to link your different elements together. I'll come back and explain that in one sec. So we start with the thing we wanted to maximize here. So the volume we want to maximize is the volume of the cylinder. And based on what we know, cylinder is pi r square h. So based on the dimensions given in the question, r is x, h is y, so pi x square y. So this is what I meant when I said there could be multiple variable in the expression. So now you've got x and y. Yeah, that's a multiple variable expression. So you need something that link x and y together before you can go ahead and differentiate it. And that is why knowing what you're shooting for helps immensely. Before we do that, let's have a look at the diagram. So there are actually three triangles, three right angle triangle here. So one here, so a little one here, another little one here, and the big one here. And quite often, people forget about the big one. Just writing in some dimensions. So this is a rectangle, so that should be y because opposite sides are equal, and this should be x, opposite sides are equal. And if this is x and this is r, that must be r minus x. And same here, if this is height, h, this is y, this is h minus y. Okay, so now once you know which dimensions you're looking at, I'm actually going to quickly draw up the three triangles you'll be looking at. Alright, so if you pull apart the triangles, so you get this one here, this one down here, and the big one as I said. So all three are similar to each other, and in the context of a maximization minimization problem, you are not required to prove similarity. You can just use the similar relationship. Now this is where before you actually try to attempt this, look at what you're shooting for. If you look at the question, there's an r minus x component in there. And if you look at the diagram, r minus x is in this triangle or this one. So you definitely should use that one for obvious reasons. And typically avoid using two small ones. Try to use a small one and the big one, because the big one often is the cleanest one with straightforward numbers. Alright, so those are the two we're going to use, and let's draw the relationship between the sides. So what we can say is y on h is equals to r minus x on r. Because in similar triangles, corresponding sides are in the same ratio. That means y is equals to h on r, so multiplying the h across, you get that. Okay, and then finally, substituting that into our multiple variable expression, we get pi x squared, y, which is h on r, r minus x. And then that's pretty much it, that's it. So I'll just clean it up a bit so it looks exactly like the question. And that is it. Okay, so now we've got something that matches the question. We are complete. Let's move on. Alright, so now that we've answered the first part, let's have a look at the second part. Now in any exam, if you can't do the first part, which is 3 marks, move on to the second part, which is 4 marks. Yeah, you can do the basic derivative stuff. Yeah, very easy to pick up some easy marks there. So the question is, by considering the inscribed cylinder of maximum volume, show that the volume of any inscribed cylinder does not exceed 4/9 of the volume of the cone. Alright, so it's a very tricky question because it doesn't actually explicitly tell you to find the maximum volume, but it's a relationship we'll have to establish once we found the maximum volume. So let's take a look how we do that. Alright, so in part B, we're going to start with the expression. Before we differentiate this, it's important you identify your constants and your variables. Your variables are your x's. Constants are everything else, so your h, r, pi, r, okay? Constants, so you treat them like your 2's and 3's and 4's when you differentiate this. Now, to make this a little bit easier to differentiate, I'm going to expand this into the bracket, so it looks like this. Okay, now why I've done that is because that's a constant. So it doesn't really affect your differentiation, and it makes it easier for us to solve later as well. So if it's constant, just keep it up front. What you're really doing, you're just differentiating what's in the bracket. Alright, so finding the first derivative, that's our first step. So dv dx, this gives us clarity that we're differentiating with respect to x, so only the x's get differentiated. So differentiating x squared becomes 2x, differentiating x cubed becomes 3x squared. And just simplifying that. Okay, so now let's actually find the maximum, and in fact we're going to have to show that it's a maximum as well. So just like how you were finding turning points for curve sketching, that's exactly the process you're going through. So we are going to solve dv dx to 0. So in other words, we're solving that expression. To 0. And you can see why the constant is irrelevant. You're going to solve it to 0. So we're just solving that to 0. And I'm just going to factorize it. So in other words, x is equal to 0, or x is equal to 2r on 3. Obviously, x equals 0 does not make sense. You don't have a cylinder. So therefore, it's 2r on 3. Okay, so now that we've got the point at which is supposed to be a maximum, we are then going to show that it is a maximum. Okay, so now that we've got the point at which the stationary point is going to be, we need to show that it's actually a maximum turning point. As I've mentioned before, you can use a table of values, so exactly like what we did with curve sketching, or use the second derivative. And in this case, it's actually quite easy to differentiate that one again. So we are going to use the second derivative. Alright, so find second derivative. So I'm just going to grab this expression. Just copying that across first. And then we are differentiate that again. So the constants stays put, you're only differentiating the inside. Yeah, so 2rx just becomes 2r, and that one bring the 2 down, so 3 times 2, 6x. And once we've done that, we are testing this point. We want to show this is a maximum turning point at this point. So sub x is equal to 2r on 3. Let's see what we get. Okay, so you evaluate this, it actually becomes minus 2r. So minus 2h pi. Obviously h and pi are positive numbers, so therefore this is negative. And remember what that means. A second derivative that is negative means it's a concave down turning point, so it's a maximum turning point. So therefore it's gonna be like that shape. So maximum turning point at x is equal to 2r on 3. And that is it. So far all we found is that at x is equal to 2r on 3, that's when the volume is going to be maximized. So how do we actually address the question? Because that's not the question. The question is show that the maximum volume, so this one here, is not going to exceed 4/9 of the volume of the cone. So the volume of the cone being the volume of that big cone here where the cylinder is inscribed. So we're going to take a look at how to approach that part. Now that we've found the point at which the volume is maximized, let's answer the question. So to summarize, we've got the volume equation here, and we've established that the volume is maximized at 2r on 3. So let's go ahead and find the maximum volume first. So sub that into that, we get this expression. Evaluate everything, just clean up the expression a little bit. And then just simplifying everything. So let's cancel that. So for 4 on 27, basically, pi r squared h. And let's label that as max. Okay, so now that we've got the maximum volume of the cylinder, let's compare that to the volume of the cone. So if you recall, the cone had dimensions h and r as the radius. So the volume of a cone is 1/3 pi r squared h. So we're comparing that to that. So in other words, the volume of the cylinder to the volume of the cone is 4 on 27 pi r squared h to 1 on 3 pi r squared h. So you can see pi r squared h is almost irrelevant here. They are just ratios of pi r squared h. And I'm just going to quickly fix up this ratio and divide everything by 3. So it's 4 to 9. Okay, which is exactly what we were looking for. So therefore, just going back and address the question, therefore the maximum volume of the cylinder does not exceed 4/9 of the volume of the cone. And that is it. Now that is it for this video, but if you would like to see another problem in this area of application of calculus to maximization and minimization problem, I've created a part 2 to this particular video. In that video, I'll be going through this particular problem where it looks at the relationship between speed, distance and time. Thank you for watching. If you like this video, please give me a thumbs up and subscribe to my channel. I'll see you soon.